Welcome to our deep dive into differential privacy in machine learning with TensorFlow Privacy. In this video, we'll explore what differential privacy is, why it's important, and how you can implement it in your machine learning models using TensorFlow Privacy. Whether you're a developer, data scientist, or just curious about how machine learning protects sensitive information, this video will break it all down for you. First, let's start by understanding what differential privacy is. In simple terms, differential privacy is a technique that allows machine learning models to learn from data without revealing sensitive information about individual data points. Imagine you're training a model on user data. Without differential privacy, there's a risk that the model might memorize specific information, which could lead to privacy breaches. Differential privacy addresses this by adding controlled noise to the data, which ensures that individual user information remains private while still allowing the model to learn useful patterns. Differential privacy works by making it difficult to determine whether any individual data point was included in the dataset, even with access to the model's outputs. This concept is critical in preventing attacks like membership inference, where an adversary tries to determine if specific data was part of the training set. By adding noise to the data or the model's gradients, differential privacy ensures that the influence of any single data point is limited, making it practically impossible to extract individual information. Why is differential privacy important? In today's world, data privacy is a top concern, especially with increasing regulations like GDPR and CCPA. Organizations need to ensure that personal data is protected, even when used for training machine learning models. Differential privacy helps strike a balance between data utility and privacy, making it possible to use data to train accurate models while minimizing the risk of exposing personal information. By incorporating differential privacy, organizations can build user trust, comply with legal requirements, and maintain a competitive edge in a privacy-conscious market. Now, let's talk about TensorFlow Privacy, an open-source library that allows you to integrate differential privacy into your machine learning models. TensorFlow Privacy is built on top of TensorFlow and provides easy-to-use tools to add differential privacy to your training process. This way, you can ensure that your model adheres to privacy standards and protects user data throughout the training process. TensorFlow Privacy includes functionalities that allow developers to easily add noise to gradients and clip gradients during training, making it accessible even for those who may not be privacy experts. One of the core concepts behind TensorFlow Privacy is the addition of noise to the gradients during training. When training a model, gradients represent how much each parameter should change to reduce the error. By adding noise to these gradients and applying clipping, TensorFlow Privacy ensures that the model doesn't rely too heavily on any single data point, thereby enhancing privacy. This technique helps keep sensitive information hidden while still allowing the model to learn effectively. Gradient clipping also limits the influence of any single data point, which is crucial for maintaining privacy while training on sensitive datasets. Let's walk through an example of how you can use TensorFlow Privacy in a typical machine learning project. Suppose you're training a model to predict user behavior based on activity data. Without differential privacy, the model might inadvertently memorize unique characteristics of individual users. By using TensorFlow Privacy, you can set privacy parameters, like the amount of noise added in the gradient clipping level, that control how much influence each data point has on the model. This approach limits the risk of any single user's data being exposed and helps you comply with privacy regulations. To get started, you would first import the TensorFlow Privacy library and modify your training loop to include privacy-specific optimizers. TensorFlow Privacy provides DP gradient descent and other optimizers that handle noise addition and gradient clipping automatically. You can also adjust parameters such as the noise multiplier and clipping norm to control the level of privacy. By experimenting with these parameters, you can find the best balance between model accuracy and privacy protection. TensorFlow Privacy also helps you quantify privacy through a metric called epsilon. Epsilon measures the trade-off between privacy and model accuracy. A lower epsilon value means better privacy, but it may come at the cost of model accuracy. It's up to data scientists to find the right balance, depending on the use case and the level of privacy required. TensorFlow Privacy provides tools to help tune these parameters and evaluate the privacy guarantees of your model. Understanding epsilon is key to implementing effective differential privacy. Too low, and your model may struggle to learn. Too high, and privacy may be compromised. The adoption of differential privacy in machine learning is crucial for industries that deal with sensitive data, such as healthcare, finance, and social media. For example, imagine training a model to detect health patterns using patient data. Ensuring differential privacy means that no individual patient's data can be traced back, which is vital for maintaining trust and adhering to privacy regulations. TensorFlow privacy allows developers to implement these protections without needing to redesign their entire machine learning pipeline. In finance, differential privacy can help banks and financial institutions analyze customer data without risking privacy breaches, allowing for better fraud detection and customer insights while keeping data secure. Let's also address some of the challenges of using differential privacy. One of the biggest trade-offs is the potential loss in model accuracy. Adding noise to protect privacy can make it harder for the model to learn, especially if too much noise is added. Finding the right balance between privacy and accuracy requires experimentation and tuning, but TensorFlow privacy provides practical tools to guide this process. Another challenge is computational overhead, as implementing differential privacy can require more resources compared to standard training. Training with differential privacy may take longer due to the additional noise and clipping operations, but the benefits in terms of privacy protection often outweigh the increased computational cost. It's also worth noting that different applications may require different levels of privacy. For example, a social media platform may require a different privacy accuracy balance compared to a healthcare application. Understanding the specific needs of your application is crucial in determining how to set privacy parameters effectively. TensorFlow privacy's flexibility allows you to experiment and tailor the privacy settings to meet the unique demands of your use case. In conclusion, differential privacy is a powerful tool that allows machine learning models to learn from data while protecting individual privacy. TensorFlow privacy makes it easier for developers and data scientists to add these privacy-preserving techniques to their models, ensuring compliance with privacy regulations and building user trust. As privacy concerns continue to grow, adopting technologies like TensorFlow privacy will be essential for responsible AI development. By leveraging TensorFlow privacy, you can build machine learning models that are both effective and respectful of user privacy, setting a new standard for ethical AI. Thank you for joining us on this journey into differential privacy in machine learning with TensorFlow privacy. If you found this video helpful, make sure to like, share, and subscribe for more insights into privacy-preserving machine learning techniques. Let us know in the comments, have you used differential privacy in your projects? What challenges did you face, and how did you overcome them? We'd love to hear about your experiences and any tips you might have for others exploring this technology.